In this video, we will see the modeling of few first-order physical systems. We will start with a liquid level system. We have an inflow, volumetric flow of the liquid Q of T into the tank, and H of T is the height, the liquid level in the tank, and R is a resistance. It can be a valve, pipe, etc. And Q naught is the volumetric flow of the liquid, outflow of the liquid. So the rate at which the liquid is flowing out. And A be the uniform cross-sectional area of the tank. So we assume here that a resistance that has a linear relationship between the flow and the head is referred to as a linear resistance. And here we assume that we are considering a linear resistance. Now a pipe is linear resistance if the flow is in the laminar region, and turbulent flow through the pipes and valves is generally proportional to square root of H. So we are not considering here the turbulent flow, we are considering here a laminar range or a linear resistance. And rho is the constant density of the liquid. Now here we will start the modeling by using the transient mass balance around the tank. The mass balance around the tank shows the rate of mass flowing into the tank minus the rate of mass flowing out of the tank is equal to the rate of accumulation in the tank, accumulation of mass in the tank. Now here some liquid is flowing in and some liquid is flowing out. So the rate of the mass accumulation in the tank, the rate of change of mass accumulation in the tank will be equal to whatever is coming in and whatever is minus whatever is leaving out. This is equal to density into volumetric outflow, volumetric flow of the liquid. So that is the rate of mass that is coming in, and density into a volumetric outflow of the liquid, that is the mass flowing out, and d by dt of rho AH, that is the rate of accumulation in the tank, where A is the uniform cross-sectional area of the tank and H is the height of the tank. Since rho and area are constants, we can take it out, and this will be equal to rho A dH by dt. Can cancel off the rho in all the three terms, and the equation will become Q of T minus Q naught of T equal to A dH by dt. Here Q is dependent on the time, it varies with respect to time, and the outflow also varies with respect to time, and the height H is also varying with respect to time. Now this outflow, volumetric outflow, will depend on the height of the liquid as well as the resistance of the outflow. So it is equal to Q naught is equal to H by R. So it is directly proportional to the height. So if the height is very high, then the amount of liquid that is flowing out will be more. And if the resistance is very large, the amount of liquid flowing will be less. So it is height is directly proportional to the outflow and resistance is inversely proportional to the outflow. So the equation becomes Q of T minus H by R equal to A dH by dt. Now, the first step in analyzing the model of a system is to analyze the process operating at steady state. Steady state means there is no change. So here in this equation, if at steady state, this value will become 0. So the process operating at steady state will have all the derivative terms 0. So at steady state, this above equation becomes, so at steady state it becomes Qs minus Hs by R equal to 0. Now at steady state we have a fixed height, that height is Hs, and we have a fixed inflow Qs. Now subtracting equation 2 from 1, we will get Q minus Qs is equal to 1 by R H minus Hs plus A d H minus Hs by dt, where all the S subscript shows that those are in steady state value. Now we define Q, capital Q as Q minus Qs and capital H as H minus Hs. Now this equation after substituting will be Q equal to 1 by R H plus A dH by dt. Now taking Laplace transform on the both sides, we will get Q of S is equal to 1 by R H of S plus AS H of S. Here the derivative will contribute this S term. Now our aim is to find a model. Model means the relation between output as the input. Here the output is H of S, the height of the tank, and input is Q of S, the inflow of the tank. So that will be related as R by tau S plus 1, where tau is equal to AR. It is a constant value tau. So this is a first order system. This is how we model a first order system. It's a single tank liquid level system. Now we will see a slightly changed system where the level process with a constant outflow. So the output flow Q naught is a constant now. It's a fixed value now. To show that I have placed a pump here. So we are taking out the liquid at a constant rate. So here again Q of T that will be varying with time, and the height of the tank that also will be varying with time. So we will see how we can model the system. What is the relation between the input Q of T and the output H of T? By mass balance equation, by transient mass balance equation, we write Q of T minus Q naught equal to A dH by dt. Here I am not writing Q naught that is varying with time because it is a constant value. So it doesn't vary with time. So Q of T minus Q naught is equal to A dH by dt. Now again we will analyze first at steady state. So in the above equation, dH by dt will be 0 at steady state. So there is no variations at the steady state. So this dH by dt term will become 0. So Qs minus Q naught will be equal to 0. Nothing but Qs equal to Q naught at steady state. Now subtracting this second equation from the first equation, we get Q of t minus Qs equal to A dH by dt. Now take capital Q equal to Q minus Qs. Those are called deviation variables. So we take this together as capital Q and A d capital H by dt. We take H also as H minus Hs. Now Q equal to A dH by dt. Now applying Laplace on both sides and getting the relation rearranging, we get H of S by Q of S is equal to 1 by AS. So this is the model of this particular case, special case where the outflow is a constant value, Q naught is a constant value. Now we will see another process, the mixing process. So how to model a mixing process? Here we have liquid coming into the tank with some concentration of salt that is entering the stream. And we have liquid that is flowing out of the tank with some different concentration, say Y of T. Now, X of T is the concentration of the salt in the entering stream, where X is mass of the salt divided by volume. That varies with time. The salt concentration varies with time. And the outlet concentration is Y. That also varies with time, Y of T. And V is the constant hold up volume. So the volume of the liquid that is in the tank, that is a fixed value, that is V. And the inflow, constant volumetric flow rate. The inflow is also constant Q. That is the same flow rate as the outflow. So that is how there is a constant hold up volume. So there is a fixed rate of inflow, there is a fixed rate of outflow, but the salt concentration of the inflow and the salt concentration of the outflow are different. And we use a stirrer to maintain the salt concentration within the liquid as a fixed value. Now to model this, we use transient mass balance for salt. So the transient mass balance for the salt is flow rate of the salt into the tank minus flow rate of the salt out of the tank is equal to the rate of accumulation of the salt in the tank. So Qx minus Qy equal to dVy by dt. So since V is a constant, we can also write V into dy by dt. Now at steady state, all the variations will be equal to 0. Qxs minus Qys equal to 0. S represents steady state. Now subtracting equation 2 from 1 and taking the deviation variables x minus xs and y minus ys as x and y respectively. After substituting, we get qx minus qy equal to v dy by dt. Now take the Laplace transform on the both sides and rearranging, we get the relation between the output salt concentration and the input salt concentration. So y of s divided by x of s equal to 1 by tau s plus 1. This is also a first order system where tau is v by q, that is a constant value. So this is how we model a mixing process. We will see more complicated modeling of more complicated mixing process later. So another example of a first order system is a heating process. So we have a single tank where we have stream at temperature Ti is fed into the tank. Heat is added to the tank by means of an electric heater, and we assume the flow rate to be a constant value W. So Ti is the temperature of the stream that is coming into the tank, and capital T is the temperature of the liquid that is flowing out of the tank. And Q, there is a heat added to the tank as well. So here we model the system using transient energy balance equation. So we balance the energy. So rate of energy flowing into the tank minus rate of energy flowing out of the tank plus rate of energy that is coming from the heater is equal to the rate of accumulation of energy in the tank. So Wc into Ti minus Trf minus Wc into T minus Trf plus Q equal to rho Vc d by dt T minus Trf. Here Trf is the reference temperature and C is the heat capacity of the fluid. At steady state, we will have all the derivative terms as 0 and we get Wc Ti s minus Ts plus Qs equal to 0, where S is steady state value. Subtracting this second equation from the first equation, we get Wc Ti minus Tis minus Wc T minus Ts plus Q minus Qs equal to rho Vc d by dt T minus Ts. Introducing the deviation variables T dash equal to T minus Ts and capital Q equal to Q minus Qs. After rearranging, we get minus Wc T dash plus Q equal to rho Vc d T dash by dt. Applying Laplace transform on both sides, we get minus Wc T dash of s plus Q of s equal to rho Vc s T dash of s. After rearranging, we get the relation between the output and the input. T dash of s by Qs. It will be equal to 1 by Wc divided by rho Vw s plus 1. So when you see closely, it is also a first order system of the form k by tau s plus 1. So these are few examples of a first order system. We have only considered the linear systems. We will move on to more complicated systems in the next videos. Thank you.